Yes, sir.
Right. Thank you very much. So, good morning, all of you. Today, we are in the third unit of Water Resources Engineering 2. The third unit consists of two parts, earth dams and spillways. In the previous classes, we discussed and completed about the earth dams. In today's class, we are now ready to take up the spillways. So in this spillways, as per our syllabus, we will be looking into the types of spillways, design principles of ogee spillway is a special type of spillway, one type of spillway. We will see other types of spillways also for the discussion in types of spillways, followed by gates which are provided for the spillway and how the energy gets dissipated in the spillways and the requirement of the stilling basin and the significance of the jump height curve and tailwater rating curves and USPR and Indian types of stilling basins which are provided at the downstream portion of the spillway for dissipation of the energy. So we see about these topics in the subject spillways we try to look at and define the spillway functions, types, and more particularly about the ogee shaped spillway and the design procedure for obtaining the ogee profile, what we need to do, we will study. So what is the spillway? Spillway is the overflow portion of a dam. So the dam may be any type, maybe arch dam, maybe buttress dam, maybe earth dam, maybe a gravity dam. For any type of dam, for the safety of the reservoir and the dam structure, to release the excess flood to the downstream portion, this is spillway we provided. This is the overflow portion of the dam. By providing the spillway, the dam and the reservoir becomes safe. If a dam is provided with no spillway, what might happen, because there is huge flood during the some parts or some period during the life of the dam and the reservoir, more flood water joins and the water level raises over and above the maximum water level. Then the water which comes into the reservoir has to let off to the downstream, so it starts overflowing. In the process, the dam may fail. So to have a safety precaution, the excess water must be disposed to the downstream portion safely by providing a spillway. So this is called the safety valve also. The spillway is also called the safety valve. You can see here in this picture the clear demarcation of a spillway and a dam. Dam provided with the sluice gates and the spillway. Thereby, the excess water which is coming in the reservoir is let off to the downstream portion in a safe way. Let us see this video which depicts you the flow of water, flow of excess water from the reservoir to safeguard the dam and the reservoir. So we have seen the floods and how the floodwater is getting disposed from the reservoir. We know the importance of floods and the ill effects of the floods we have been experiencing, particularly in the city of Hyderabad for the past 2 days, and in the entire states of Telugu states of Telangana and Andhra Pradesh also. Let it be an urban area, let it be a rural area, let it be a catchment area, let it be an irrigated area, let it be a dam reservoir. There is no distinction for the flood, there is no distinction for the rainfall. So that is the reason we must have seen in some of the areas, particularly in the Hyderabad city, lots of WhatsApp videos also are moving, saying that no, the vehicles, four-wheelers are just floating on water. Also, similarly, the buildings are getting collapsed, people died, all these are happening. Flood management is a very big subject. Managing the flood is a bigger task. As far as our subject is concerned, we are trying to manage the flood with respect to the safety of the reservoir. With respect to the safety of the reservoir, this is all the nature. You see, when we want water, probably there may be no rainfall. When we don't want water, also there will be rainfall. There may be huge rainfall, which may create a lot of havoc, disturbing the normal life of the public. So all the things will be happening. So what we need to do is we need to understand how to manage the flood. Urban flood management is once again another big chapter. One of your senior also has carried out a small project work under me last year to manage the urban flood, particularly Hyderabad city, and what are the possibilities of the urban floods, and how to estimate the flood and how to manage the flood. So this is all a bigger subject which directly depends on the rainfall. So proper drainage is one system, and the other thing is that so providing good tanks at several places where the tanks are already available must be restored to see that all the flood water is absorbed and stored there. So there are several ways and means through which the flood management can be taking place, particularly in the rural areas. The farmers who are directly depending on the rainwater or the water which is coming to them through the canals, and they feel very happy if water is coming to their fields. But at the same time, they will be unhappy if there is no water. They will be unhappy if more water is there. See, the situations would be like this. So if more water is there, what will happen? Entire irrigated land will be completely flooded. They must have invested from the month of June, starting of the monsoon period or starting of the Kharif period. They must have invested a huge amount in terms of plowing, then in terms of sowing, in terms of keeping the pesticides, everything. They must have invested huge, looking at the crop and its growth. They feel very happy. But at the verge of going for the harvest, maybe another 20-30 days would have been enough for the farmer to harvest the crop and get some benefit out of it. But in the meantime, what happened? Big flood has come, and all these floods have created a havoc situation where entire irrigated land has been completely submerged. Because of the submergence, what will happen? The plant which is about to raise or which is about to harvest definitely will be spoiled, and the net profit that he would get would be minus, negative, because he's already invested. He's not getting anything. So this is all the pathetic situation of the agricultural farmers. So this is to be controlled. But as I told you in the first class itself, you can't control the rainfall. But what you need to do is we have to manage the rainfall. We have to manage the floods to see that the farmers are kept at a comfortable position, to supply water as and when required, not to supply water when it is not required. So you need to make certain preventive and protective measures to see that the floodwater is completely controlled without submerging the irrigated land. This is all required, and this to be done by the irrigation engineer. So to have a good safety for the entire reservoir and the dam and the corresponding downstream portions, spillway is one of the requirement for any of the dam project. What is this spillway? Let us start from the simple definition of a spillway: a structure constructed at a dam site for effectively disposing the surplus water from upstream to the downstream portion. A dam with no spillway leads to a lot of complications. It may lead to the failure of the dam on one side. It may lead to the failure of the entire project, reservoir project on the other side. Also, On the third side, because of this water level rising abnormally, on the upstream side, a lot of submerges may take place, and the downstream side, a lot of flooding may take place. So there is a dire necessity of providing this structure, namely spillway at a dam site. So spillways necessarily to be provided at a dam site for effectively disposing the surplus water, excess water which is coming into the reservoir must be disposed safely to the downstream portion, from upstream to the downstream portion. This is what the definition of a spillway. The spillway starts functioning when the water level rises above the maximum water level in the reservoir. So till such time, what will happen? The water joins the reservoir, and the water gets stored in the reservoir, which is required for us. Any storage reservoir requires the water to be stored. For example, if you take Nagarjuna Sagar, maximum water level is plus 590. Till such time, the water will be stored safely. But over and above 590, we should not store the water. So it has to be safely let off to the downstream portion. So hence, a spillway is a safety wall for a dam. If you see here in the right side picture, you must have seen these are all the gates which are provided for this spillway. Over the crest level of the spillway, the gates are provided. So depending on the inflow that is coming into the reservoir, inflow flood that is coming into the reservoir, the gates will be opened, and which allows the water to flow to the downstream portion. Thereby, maximum water level on the upstream side in the reservoir will be safely maintained. On the left hand side, we have the figure here that this also is a spillway with the gates. Spillway with gates, but there is no water flowing to the downstream portion, which means that the water in the reservoir on the upstream side is much lower than the maximum water level. So this is a spillway. This is the spillway. In this case, this is a spillway which is under operation. This is a spillway which is not being operated because there is no heavy flood into the upstream side into the reservoir. The spillway is designed for the maximum estimated flood. I'd like to draw your attention once again. What do you mean by this maximum estimated flood? So first of all, flood water, when entering into the reservoir, we try to store the water. We try to store the water till such time it reaches the maximum water level MWL or nearer to that. We try to store the water. So when excess water is coming into the reservoir, that means you need to estimate how much flood comes here. You need to estimate how much flood comes into the reservoir. How this estimation will be taken up? Once again, there is a separate subject. How much catchment area is there? What is the maximum catchment area? And what are the coefficients? You may use any of the standard formula. You may use the GIS to find what would be the estimated flood, or some modeling techniques can be done. So a rough estimate always can be taken up by the studies based on the past or history of the flood in that area. Based on the history of the flood in that area, because as a water resources engineer, we always presume that there will be reoccurrence of the events. Say flood event, maximum flood event is occurred maybe during the last 50 years once. We assume that in the coming 50 years also, same maximum flood may occur in the coming 50 years. So this is what, based on the recurrence, we try to estimate the maximum flood. And there are various other crude methods, also rough estimation methods are there. Nowadays, we can make use of the GIS technology to find out the exact prediction of the flood that may be entering into the reservoir. So for this maximum estimated flood, the spillway is to be designed. The spillway is to be designed. That means when you open the gates, all this maximum flood which is coming must be safely disposed to the downstream portion over and above the maximum water level. It must have the capacity to discharge the design flood without causing damage to the dam. This is the main purpose. If there is any damage to the dam, the purpose will be defeated. The purpose will be defeated. Entire structure will be unnecessarily cannot be used because there is a damage for the dam. So we need to ensure the safety of the dam. So without causing a damage to the dam, it must discharge the entire flood. And it is observed that most of the dams have failed due to provision of inadequate spillway. That means the spillway is designed, spillway is provided, the spillway is designed, the spillway is provided, but the capacity the discharge capacity is not sufficient to cater the needs of the maximum flood coming into the reservoir. So even if all gates are open, still water level is rising, which means that it has not been properly designed for its maximum estimated flood. Therefore, a spillway with adequate capacity is a must for any storage dam. When you're constructing a dam, it is necessary that you should have the spillway with a sufficient capacity. So where is this spillway located? A spillway can be located either in the body of the dam, as we have seen in the previous figures. It may be within the body of the dam, or at one end of the dam, or entirely away from it and independently in a saddle, depending upon the site condition. Usually for the earth dam, the spillway may be provided independently at a separate location, not directly connected with the dam. Also, earth dam also can be provided. Types of spillways. What are the various types of spillways? The spillways are classified like main spillway, subsidiary spillway. Subsidiary spillway is also called the emergency spillway. The main spillway is the one which is called upon to work under design floods. So maximum estimated flood is the design flood for which the spillway is designed. So it is called designed flood. So maximum estimated flood is the design flood for the spillway. So usually the main spillway is designed for the maximum estimated flood. Emergency spillway also will be provided in certain cases to provide additional safety to the entire dam reservoir project when a flood greater than the design flood occurs, or when the main spillway gates fail. Sometimes there is a possibility that the flood which is coming into the reservoir may be more than the design flood, more than the maximum estimated flood, because we're all taking simple statistical principles. For the past 50 years, what is the maximum flood? Maybe for the coming 50 years, what would be the maximum flood? We assume that there will be the same flood may recur, and we try to design for the same maximum capacity. In certain extreme cases, like we have experienced in Hyderabad during the last 3-4 days, and this type of flood was never estimated, never known also. So like this, in these certain special cases, the flood may exceed the maximum estimated flood also. So since the spillway is not provided for more than the maximum estimated flood, that means more than the design flood, naturally there will be a problem. In such case, this emergency spillway will be put to operation. There are certain other cases also. Spillway always will be provided with the crust gates. So if you open the crust gate, naturally over and above the crust level, whatever is the water is there, which is being safely disposed to downstream portion. But what is the special case? Sometimes in the emergency, the crust gates may fail. You have seen in the previous figures, there may be spillway with some 70 crust gates, 50 crust gates, like that. So in which say 5-6 crust gates fail. What will happen? You are not able to lift the crust gate. You are not able to allow the discharge to flow. Though the spillway is designed for the maximum flood, because of the failure of the gates, there could be possibility for the failure of the dam and the entire dam reservoir project. So to avoid this situation, the emergency spillway will be provided. Under normal operation, emergency spillways are not required to function. Emergency spillways are provided for the earth and rockfill dams to avoid overtopping. If there is any failure of the spillway or a spillway gate, then there will be a problem with more and more flood water getting stored in the reservoir, water level rising, and then leading to the failure due to the overtopping. So to avoid this problem, this emergency spillway in the earth dam or a rockfill dam provides additional safety for the earth dam. Next category is controlled spillway, uncontrolled spillway. The flow of water over a spillway may be controlled by installing the gates over the spillway crest, which we have been discussing. Such a spillway is known as controlled spillway. Over the crest, gates are provided, and these gates will be under closed condition usually, so that on the upstream side the water will be stored. As and when more flood water is into the reservoir, the crest gate will be opened, allowing the water to flow to the downstream portion. So this is what is called controlled spillway. When gates are not provided over the crest of the spillway, then it is called uncontrolled spillway. A controlled spillway has got more flexibility of operation, gives better control, increased usefulness of the reservoir, because you are storing the water to the maximum extent possible in the reservoir by providing the crust gates. So if in the case of uncontrolled spillway, since there are no gates provided, automatically the water over and above the crust flows to the downstream portion. You may require little more water over and above the crust, but it will not be available because it flows directly to the downstream portion. This is the uncontrolled spillway. Depending upon the type of the structure constructed for disposing the surplus water, the spillways are classified. This is the next classification: straight drop spillway, ogee spillway, also called the overflow spillway, then chute or open channel or trough spillway, side channel spillway, shaft spillway, siphon spillway, depending on the process and what type of structure is provided and how the water, excess water is getting disposed, the mode through which the excess water is getting disposed to the downstream. So the spillways are classified: straight drop spillway, ogee spillway, chute spillway, then side channel spillway, shaft spillway, siphon spillway. Let us see one by one. But we take up two in today's class, like straight drop and ogee spillway. What is this straight drop spillway? Simplest type of the spillway may be constructed on small bunds or thin arch dams, and it is a low weir having downstream face either vertical or nearly vertical. It directs the small discharges away from the face of the overflow section, thereby the excess water flows to the downstream. Straight drop spillway, like a weir is there, a weir wall is there. Over and above this crest level of the weir, what all the water which is coming flows to the downstream portion in the form of a nappy. This is the sheet of water which is falling to the downstream portion. A solid wall, over and above this crest level of this solid weir wall, the excess water flows to the downstream in the form of a sheet of water known as nappy. So this is the lower nappy, this is the upper nappy. So this is the flow of water. This is called the straight drop spillway. There are certain advantages, there are certain disadvantages. Simple in construction, may be used for any of the small discharges and so on. But the disadvantage in this is, as we have seen in our fluid mechanics second year, there would be a problem when the water is flowing continuously to the downstream portion like this. In this portion, the pressure drops below the atmospheric pressure. Because the pressure is dropping below atmospheric pressure, this nappy always will have a tendency to directly connect to the downstream face of the weir wall, leading to excessive forces and failure of the weir. So to avoid this, ventilating the weir is very, very important. In second year fluid mechanics, you must have studied about the ventilation of the weirs. Of course, this is another mode that we are providing, a small lip at the downstream portion of the spillway, downstream portion of this weir wall. Small lip is provided. The purpose of providing this lip is that this is sheet of water, the nappy which is coming here is spreading a little far from here. If it is properly ventilated for small discharges, the straight drop spillway will be highly effective and highly functional. See the picture of a straight drop spillway. You can see here the sheet of water is falling, the water is stored up to this level, over and above that it is flowing. And in this case also you may see a straight drop spillway. So the water is stored here. The blue shade here is the storage of water. As and when the water level is moving over and above this crest level, the water is falling onto the downstream portion in the form of a sheet. Only difficulty in the straight drop spillway is that it should be properly ventilated. Otherwise, a clinging may take place where the sheet of water may directly be in contact with the downstream face of the weir, leading to the failure. The second spillway is the ogee shaped spillway. The most common type of the spillway provided on the gravity dams, arch dams, or buttress dams also. It can be used on the valleys where the width of the river is sufficient to provide the required crest length. So this ogee shaped spillway will be provided on the valleys. Width of the river must be sufficient to provide this crest length also. So in addition to providing the non-overflow portion of the dam, we need to have this overflow portion of the dam also. So if the length of the crest is more, what will happen? The length of the crust multiplied by the height of the crust gives you the cross-sectional area of the flow passage, multiplied with the velocity of flow gives you the discharge. So this spillway must be able to discharge the maximum estimated flood which is coming into the reservoir to the downstream portion. So you must have sufficient length of the crust. Ogee spillway is an improvement upon the straight drop spillway. The straight drop spillway, which we have seen in the previous case, now this is the ogee shaped spillway, which is an improvement for the straight drop spillway. The profile is also known as the S curve or a parabolic curve, since the falling nappe takes the form of parabola. In the previous case, you can see here in the figure, this is the falling nappe. So this nappe is having the lower and upper surfaces, and in between there is a gap. So what will be done in the case of ogee spillway is that all this portion also is provided with a solid structure. So you have a parabolic shape for this lower nappe. So same thing is directly taken as the downstream face of the spillway. So the profile is also known as S curve or parabolic curve, since the falling nappe takes the form of a parabola. This maximum head is called the design head, and the negative pressures cause cavitation, and hence they should not exceed 4.5 meters. On the other hand, if the head on the spillway is less than the design head, the lower nappe adheres to the crest, creating the positive pressures, thereby reducing the coefficient of discharge. So we need to provide the design head, and corresponding to that, we have to see that there is no cavitation which is occurring because of the presence of the negative pressures. So this precaution is required to be taken. You can see a simple shape of a ogee shaped spillway is provided here. Because of the excess flood which is coming from the upstream to the downstream portion, the nappe is formed. So this nappe has got upper surface, and lower surface. What is required to be done in the case of a ogee shaped spillway is the downstream face of the spillway and the lower nappe of this sheet of water must be together. So this is how the parabolic shape is designed for the downstream profile of the ogee shaped spillway. So this is the crust level. You may observe here, this is the crust level, and the designed head for which the spillway is designed. Sheet of water falling to the downstream portion consisting of upper nappe and lower nappe. Then the upstream face mostly will be vertical. It could be even inclined also. This is a sharp crested weir with the upstream face completely vertical. You may have a spillway, ogee shaped spillway with upstream face not vertical but inclined also. Please note that point C and this origin, I mean say this is O, are different. They are not same. They are at different levels. So you have a gradual increase in the level up to the point C. From C, there is a gradual fall. This is the profile. Of the ogee shaped spillway. You can see a picture of a ogee shaped spillway in the field, how it would be. Okay, there are two bunds connected, and this ogee shaped spillway is provided. So this is the shape of the spillway. This is the ogee shape of the spillway. So when the water is flowing, the shape of the spillway appears like this. Okay, so this ogee shaped spillway, in fact, we have in our hydraulics laboratory also, hydraulics and fluid mechanics laboratory also. You must have seen a big channel. Within the channel, a red ogee shaped spillway has been prepared and it has been installed there. It was taken up as a part of one of the project sponsored by Ministry of Human Resource Development during the year 93-94 when I was a lecturer. We have taken up this project, and MHRD has sanctioned the amount for developing our hydraulics laboratory in our college. So what we have done, we have prepared the ogee shaped spillway. We have taken a wooden piece, and this wooden piece we have taken it, and on a big graph sheet, we have drawn the profile of the ogee shaped spillway. Accordingly, with the help of the carpenter, we have seen to it the shape has been arrived, which has been fitted directly in the flume, which is available in the hydraulics laboratory. Several tests can be carried out on this ogee shaped spillway. Let us see how this shape can be arrived at also in the coming discussions. Design the shape of crest of the spillway. Theoretically, the profile should correspond to the lower nappe of a free falling jet. Such a profile should cause no negative pressures on the crest under the design flight. So this is the main condition. There should not be any occurrence of negative pressure. In practice, due to friction on the surface of the spillway, negative pressure occurs. In order to avoid these negative pressures, consistent with the practicability, various modified profiles have been proposed. So Krieger's profile is one profile which has been proposed by Kriegel. This is a practical profile for the ogee shaped spillway with upstream face vertical. Also, the case is that upstream face may be sloping at 45 degrees. A table of coordinates with the upstream face vertical connecting the x and y, the coordinates of the unit head of overflow, are provided. The coordinates for any head h may be obtained by multiplying the values which are given in x and y with h. So this is how the shape of the spillway, which is the head over the crest. So to get that h value, once you know the h value, you will be able to get the coordinates. So this is the table which has been given. Multiplying the coordinates in the table by the head on the crest. Head on the crest may be varying. So based on the value of the head on the crest, which is arrived based on the maximum flood inflow into the reservoir, we will be able to arrive at the coordinates x and y. Thereby the profile can be arrived. The profile of the spillway can be arrived. So water-based experimental station WES profile. So several standard ogee shapes have been developed by the US Army Corps of Engineers at their water-based experimental station, WES profile. This is also very interesting and important profile. Water-based experimental station profile, WES profile. So such shapes are known as WES standard spillway shapes. They adopt curves whose equations contain fractional powers connecting x and y for the downstream profile. The equation is given to be x to the power n is equal to k into hd, the design head to the power n minus 1 into y. X and y are the coordinates. Of course, k and n certain coefficients here. N and k are the coefficients. X and y are the coordinates for the downstream profile, the spillway profile, and hd the design head. So this is the shape of the spillway we may arrive at, and this is the nappe. You can see here in the figure that the lower nappe is directly in contact with the shape of the spillway, downstream profile of the spillway. This is the WES profile. X and Y, the coordinates of the points with the origin at the highest point C of the crest. So origin is taken at the highest point, and HD the design head, including the velocity head, and K and N are the constants depending upon the slope of the upstream face. The values of K and N are given in a table, and this HD is the design head. It is not simply the water level over and above the crest to the maximum level, but it includes the velocity head also. Velocity head, that means velocity of approach you are considering in this case. This need not be considered in all the cases. When you have certain limitations, then only you need to go for the velocity head. Otherwise, this can be neglected also in the design. So for vertical shape, the values are given here. Upstream vertical, the value of K is 2, N is usually 1.85 as per the WES profile. Suppose instead of having a vertical upstream face for the spillway, you have a slope of 1 horizontal to 3 vertical. The values of K and N are deferred. Similarly, 1 horizontal to 1.5 vertical, the values of K and N are deferred. So different profiles are shown here. You have a vertical profile, vertical upstream face, and inclined upstream face with 1 horizontal to 3 vertical, inclined upstream face with 1 horizontal to 1.5, 1 horizontal to 1.5 vertical. According to the latest studies of US Army Corps, the upstream curve of the Ogee spillway follows this equation. Please go through this equation. Y is equal to 0.724 into x plus 27 to x plus 0.27 HD, H suffix D whole to the power 1.85. HD is the design head including the velocity head, divided by HD to the power 0.85 plus 0.126 HD. Okay, so the upstream profile with respect to point C in the figure, you can see this is the topmost point, crest of the spillway C. This is the crest, the C. This is the crest C. So the upstream profile also is there with respect to this C as the origin. You have the downstream profile. Also, you have the upstream profile. You can see this is the upstream profile. So this upstream profile extends up to a distance A given by x is equal to minus 0.27 HD. Up to that distance, it extends on the upstream side. The following table of coordinates can also be used for obtaining the WES profile with vertical upstream phase. So you have lower nappe, coordinates of lower nappe, coordinates of upper nappe, y by HD with respect to x by HD have been proposed based on the above equation. Table is prepared. The lower nappe and upper nappe can be plotted with the help of the coordinates. A smooth gradual reverse curvature is provided at the bottom of the downstream phase, which is shown here. So this is the topmost point C. With respect to this topmost point, you have the downstream profile, you have the upstream profile. Of course, one point here, at this point, at the downstream toe, there is a reverse curve. So from this point, there is a reverse curve. Okay, so this is the reverse curve to join smoothly tangentially to the downstream bed of the river. The discharge equation for this spillway is given by Q is equal to C into LE into HE to the power 3 by 2. What is Q? The discharge that can take place through this spillway. And C is the coefficient of discharge, which may be varying for the ogee shaped spillway to about 1.21 to 2.1 to 2.5. I'm sorry, it is 2.1 to 2.50. LE is the effective length of the spillway crest, and HE is the total head over the crest, including the velocity head. There are certain conditions, as I told you. The velocity approach, velocity head may be neglected. The effective length is given by LE will be equal to L minus 2 into N into Kp minus Ka into He, where Kp the pier contraction coefficient, K is the abutment contraction coefficient, because the spillway crest is provided with certain gates. From each one gate to the other gate, if you see, it moves something like channels. So you have number of abutments, number of piers which are there, based on which N is the number of piers and pier contraction coefficient and abutment contraction coefficient. So look at this equation. LE will be effective length is given to be L minus 2 into NKP minus Ka into the He, the head. The values of Kp and Ka depend mainly upon the shape of the piers and that of abutment, and are given by this table. So you have a square nosed pier, the value of Kp is 0.02, round nosed pier 0.01, and pointed nose pier 0.00. Similarly, the value of Ka, abutment coefficient, 0.2 and 0.1, depending on you have square abutment with the head wall at 90 degrees to the direction, or rounded abutment with the head wall at 90 degrees to the direction of flow. We work out a small problem making use of these details which are given for WES profile and the Krieger's profile, which are provided by US Army Corps of Engineers. Design a suitable section for the flow portion of a concrete gravity dam having the downstream face sloping at 0.7 horizontal to 1 vertical. The design discharge for the spillway is 8,000 cubic meters per second. You can imagine how much water is to be discharged by this spillway to the downstream portion. 8,000 cubic meters in 1 second. 1 cubic meter, 1,000 liters. So 8,000 liters of water in 1 second has to be discharged. That's how huge amount of flood flow takes place into the reservoirs. The height of the spillway above the bed level is 104 meters. The spillway consists of 6 spans of 10 meters width. The thickness of each pier is 2.5 meters. Assume the coefficient of spillway as 2.2 with the suitable values for Kp and Ka. Assume the values of Kp and Ka suitably, and coefficient of spillway is given to be 2.2. Okay, so the discharge equation Q is equal to C Le He to the power 3/2. So take Kp 0, Ka 0.1, and assume that Le initially to be approximately equal to L. What is the L? Total crust length. The total crust length, how do you obtain? You have 6 spans here. Each span is 10 meters. So the value of L will be equal to 60 meters. So assuming the value of C to be equal to 2.2, substituting these values, 8,000 is equal to 2.2 into 60 into He to the power 3/2. So the value of He, the head, the design head, would be equal to 8,000 by 60 into 2.2 to the power 2/3. So you're getting 15.5 meters. 15.5 meters. But what is the assumption that has been made here? We made an approximation that the effective length of the crust is equal to the actual length of the crust. The actual length of the crust. This is the approximation that you have done. So what you need to do? You have to go for correcting it. You have to go for correcting it. So if you have this He to be equal to 15.5 meters, the design head directly as HED, then what will happen? H by HD 104 divided by 15.5 is greater than 1.33. So you may neglect the velocity of approach. Correspondingly, the effective length of the nappe, effective length of the crust, Le would be equal to L minus 2 into NKP minus Ka into He. So substituting these values, the first phase, in the first trial, the value of He is how much? You got 15.5. So take that 15.5. We know it has been only based on certain assumption like Le is equal to L. Le is equal to L. So in the first trial, we made assumption Le is equal to L. Accordingly, you got the value of He to be equal to 15.5 meters. Substituting that value as 15.5 meters, get the value of the effective length 56.9 meters. Earlier, we assumed that the effective length is equal to the total length of the crust as 60 meters. Arrive at the value of He. Substituting that value of He, get the effective length Le to be equal to 56.9 meters is the corrected value. So the new value of He correspondingly, because you have got 56.9 now, Le value, accordingly if you substitute again in the same equation, the design head HD would be equal to 15.99 or 16 meters. He to the power 3/2 is equal to 8,000 by 2.2 into 56.9, or He will be equal to 8,000 divided by 2.2 into 56.9 to the power 2/3, which will be equal to 16 meters. With this new value of He, Le is once again taken to be equal to 56.8 meters. So the profile can be designed for the head. The design head HD will be 16 meters. 16 meters is the design head. So to get the downstream profile, so WES profile for the vertical upstream phase is given by the equation x to the power n is equal to k into HD to the power n minus 1 into y. For the vertical upstream phase, we have got the values from the table. K is equal to 2 and n is equal to 1.85. So substituting these values here, x to the power 1.85 is equal to 2 into k is 2. HD to the power n minus 1. HD is 16 meters. We have seen the design head. To the power n minus 1. 1.85 minus 1.85 into y. So you have got the profile now. Y is equal to x to the power 1.85 by 21. And take dy by dx. Since y is known, take dy by dx. Dy by dx is equal to 1.85 x to the power 1.85 minus 1 divided by 21.1, which would be equal to the slope of the downstream phase of the spillway, which is provided to be equal to 1 horizontal to 0.71 by 0.7. So x to the power 1.85 will be equal to 16.3. So x will be 26.68. That means the profile has to extend from the origin, which is the top of the crust or point C, to a horizontal length of 26.68 meters. Correspondingly, the value of y also can be computed from this by substituting the value of x there. Y is 20.6 meters. So the profile now can be calculated for a maximum value of 26.68 for x and a maximum value of 20.60 meters for y. Accordingly, a table can be prepared for different values of x, corresponding value of y, substituting in this equation. Substituting this in this equation, you will be getting for x is equal to 1, 2, 3, 4, up a maximum up to 26.68. Similarly, for the value of y, you'll be getting the corresponding values. If you take a graph sheet and plot this, you'll be getting the profile. You'll be getting the profile. To get this upstream profile from the point C, the upstream profile will be extending for a distance of minus 0.27 into HD. So minus 4.32. So up to a maximum of minus 4.32, you'll be able to get the values of y based on the upstream profile. So an ogee spillway is the most suitable for the gravity dams, especially when the spillway is located within the dam body in the same valley. For earthen and rockfill dams, a separate spillway is generally built in a flank or a saddle away from the main valley. So this separate spillway may be a shaft spillway, a side channel spillway, chute spillway, or a siphon spillway. These spillways we discuss in the coming class. So today we have seen about the simple introduction of the spillway, how it becomes important in a dam reservoir project, and if the spillway is not provided, what are the adverse effects for the dam, what are the adverse effects for the reservoir, what are the adverse effects for the upstream in terms of upstream submergence, in terms of downstream flights, etc. We have seen the importance of the spillway. It is called the safety valve for a spillway. Secondly, we have seen the simple definition of a spillway along with a small video. Then types of spillways on different grounds. Okay, normal spillway, design spillway, emergency spillway, and then depending on the method that is being used with respect to the location the spillways are designed are classified. And we have seen about the straight drop spillway and secondly the ogee shaped spillway. These are the two spillways that we have discussed in today's session. Ogee shaped spillway is the most commonly used spillway, and to arrive at the profile for the ogee shape at the downstream portion and at the downstream and the upstream profile with respect to the origin C, which is the crest of the spillway, whatever WS profile we have seen, and we worked out a